this next lecture on modeling and analysis of machines, let us look at how the transformation to this arbitrary reference frame is being done. The arbitrary reference frame, as we saw in the last lecture, is a reference frame that is rotating. The speed at which it is going to rotate can be considered to be anything. You can fix the speed to be 0, in which case it would then be the stationary reference frame. You can fix the speed to be anything else that is useful. Normally the useful speeds are the synchronous speed, in which case it is called as the synchronous reference frame, or in some cases, in the case of induction machine for example, where the rotor rotates at a speed different than the synchronous speed, you could have a reference frame rotating with the speed of the rotor, in which case you would say that the reference frame is the rotor reference frame. So this induction machine description that we have seen and we have evolved until now consists of a description in the so called stationary reference frame, where you have the alpha axis and the beta axis. The alpha and beta axis are both fixed to the stator and therefore they are stationary, and in this reference frame you have a stator excitation source, which you would then call as the alpha S coil, and then along the beta coil you have another excitation, that is the beta S coil, and then you have the rotor having been transformed to the stator side. It is a pseudo stationary reference frame for the rotor. So you have an alpha R coil and then you have a beta R coil. So what you would do is you would then apply a voltage V alpha to the stator and a flow of current I alpha is there. Remember, we are using the notation that if you have a voltage, the letter here refers to the stator and the letter on top refers to the rotor, and therefore we have V alpha. As far as the rotor is concerned, both the alpha beta variables which were in the rotating reference frame of the rotor have an influence on what is V alpha here. Therefore we denoted this by the symbol Vr, but then on the alpha axis of the stator, and similarly, and you have a flow of current here, that is I R alpha, and similarly you have a voltage which is V beta and then R, and a current I R beta flowing, and then you have a voltage that is V beta and then a current I beta that is flowing, and we said that dot points are here so that currents that are flowing in will cause additive magnetic field in the machine. So for this kind of a arrangement we had evolved starting from a 3-phase induction machine. We had transformed the 3-phase to 2-phase, both the stator and rotor, and then the 2-phase of the rotor was transformed to the stationary reference frame, and we arrived at a machine description which then looks like this. So you had V alpha and then V beta, V 0 and then V R alpha, V R beta and then V 0 of R as well. So what we can do is maybe let me put it as a vector V alpha and then V beta, V 0, V R alpha, Vr beta and Vr 0. So, this is the vector of inputs that are applied, 0 sequence included, and then we had this description as Rs being the stator resistance plus P times Ls, where Ls is the self inductance, and we had an expression for the self inductance. Ls is L leakage plus 3 by 2 times MSR, where MSR is the mutual inductance between the stator and the, I am sorry, in this case it is just MS, mutual inductance between the phases. And then you have 0 here, because this is a coil that is really stationary, it is not a pseudo stationary coil. And then you have between the 0 sequence component, so that is also 0, and then between the stator and the rotor, so you have 3 by 2 times MSR P, and then 0 for Vr beta, and then the last term is again 0. In the second axis we had 0 here, and then Rs plus Ls into P 0, and then 0 here, this is 3 by 2 times MSR into P, and then 0. So, for the V0 term of the stator you have Rs plus L leakage inductance P, and then 0 everywhere else. For the V alpha R term, this is a pseudo stationary coil that has been placed, the rotor has been transformed to the stator, and therefore you will have speed EMF terms. The first term then relates to the coil both on the alpha axis, and therefore this is a transformer EMF term. So, you have 3 by 2 times MSR into P, whereas the second term relates to, for this coil, what happens due to flow of current in the beta axis, and therefore that is a speed EMF term. So, you have 3 by 2 times MSR into omega r, and then you have the 0 sequence term is 0, and then you have Rr plus Lr into P, where Lr is then L leakage inductance of the rotor, that being the stator, and then 3 by 2 times Mr, and then the term here, this will be due to the beta axis. So, you have Lr into omega r, and this term is 0, and then V beta axis. So, this is minus 3 by 2 times MSR into omega r, and then this is 3 by 2 times MSR into P, and this is 0, and then minus Lr into omega r, Rr plus Lr into P, and 0. And then the last row, which corresponds to the 0 sequence of the rotor winding. So, that would be 0 here, 0 here, 0 here, 0 here, 0 here, and Rr plus Llr into P. So, this is the so called operational impedance matrix, and this multiplies the vector of currents I alpha, I beta, I 0, and then I r alpha, I r beta, and I r 0. So, this was the description at which point we stopped, and then tried to see how this description can be used in order to describe DC machines. So, now we come back to AC machines. What we want to do now, if we look at this excitation V alpha and the flow of current I alpha, They are basically excitations and the response at the frequency of the supply. So, V alpha would then have an expression like some Vm into cos of omega t, and then V beta would then be Vm into sin of omega t. All the variables here are now going to be at the frequency of the supply. The entire machine behavior is viewed from the stator terminals. If you remember back on the induction machine equivalent circuit that you would have done in your first machine course, you would have drawn the machine equivalent circuit referred to the stator, in which all the excitations, the responses are all at supply frequency, and you have a similar kind of situation here. What we want to see is how this would change if you go to a rotating frame that is now going to move. So, let us say that you have a rotating frame, a frame that has an axis here, which we will call as the D axis, and an axis 90 degrees to that, which we will call as the Q axis. This angle is of course 90 degrees, and this reference frame that is rotating at this particular instant that we have drawn this figure, this reference frame makes an angle of delta with respect to the alpha axis that is fixed on the stator. And let us further say that we now want to find out what will be the MMF generated by, let us say, the stator excitations. Forget about the rotor for the time being. Let us look at V alpha applied to the stator, V beta applied to the stator. There is a current flowing I beta and I alpha. As a result of that, there is going to be MMF produced around the machine, air gap, and we want to know what will be the MMF that is produced due to this at some arbitrary angle. Let us say that this angle is phi. So, we want to know what is the MMF that is produced at this angle phi. So, in order to do that, what we can do is to find out the MMF distribution due to this excitation in alpha, and if you remember, we had looked at the MMF generated by a distributed stator winding. It was trapezoidal in nature, and then we split it into the fundamental and Fourier series. We neglected the other terms in the Fourier series and we took only the fundamental. So, we are looking at the fundamental component alone, and that will then be the number of turns that are available here. If you call this as number of turns of the stator, or let us call it as, it is not really number of turns of the stator, let me call it as n alpha beta for the stator, and we can call the rotor turns as n alpha beta, that is to mean in the alpha beta reference frame what are the number of turns. The stator turns and the rotor turns may be different. So, if you now have n alpha beta as the number of turns in the stator, we are considering only the stator for the time being, then the MMF generated by this I alpha that is flowing in so many turns at this point phi could be written as n alpha beta multiplied by I alpha into some term which is a fixed number. Since it is going to be a fixed number, some scale factor will be involved looking at the amplitude of the MMF. However, this is enough for our equations now. This multiplied by cos phi is going to be the MMF due to this current at this angle phi, and then you have the MMF due to the flow of current in the other axis, which one can write as n alpha beta again, because the number of turns are the same in both axes, this multiplied by I beta multiplied by sin phi. So, this is then the MMF f at a particular angle phi. Please note again that this I alpha is the instantaneous value of whatever current is flowing there. So, if we have drawn this diagram at a given instant of time t, then this current I alpha is that flow of current at that particular instant, which is not the RMS value or the peak value, so to say. But now from the figure we can write phi as, this is the angle that we want to say, we can write that as delta plus this small difference, and therefore I can write this as delta plus phi minus delta. So, phi is nothing but delta plus phi minus delta, and we substitute this expression in the expression for MMF. So, what we have is f equals, let me take this n alpha beta out, and then you have I alpha cos of delta plus phi minus delta plus I beta into delta plus phi minus delta. So, that is what you have, and these expressions can be simplified again. You have phi minus delta as one group and then delta in the other expression. So, you have n alpha beta multiplied by I alpha cos delta plus cos delta cos phi minus delta minus I alpha sin delta sin phi minus delta, and then plus I beta cos delta cos phi minus delta. This is this is I beta sin of this. So, this is I beta sin delta cos phi minus delta sin A cos B, and then plus cos A sin. That is the expression you get upon expanding this MMF term. And what we can do in this is group the terms. We will group all terms that are having this in one hand, therefore, cos phi minus delta is here, cos phi minus delta is here. So, we can write this further as n alpha beta multiplied by I alpha cos delta plus I beta sin delta, this whole thing multiplied by cos of phi minus delta, and then you have minus I alpha sin delta plus I beta cos delta into sin of phi minus delta. That is what you get. So, we started out with the MMF that is produced by the coil, stator alpha coil and stator beta coil, and that MMF equation is the same as what we have derived here. However, if you look at this equation says that you can write this as n alpha beta multiplied by, let me call this term as I d and let me call this term as IQ. So, I have ID cos phi minus delta plus IQ sin phi minus delta. Now, let us look at the first expression. The first expression says that the MMF is produced, MMF at this angle phi is given by some maximum value of MMF around the circumference multiplied by cos phi. It is multiplied by cos phi because this MMF source, which is the flow of current in this coil along the alpha axis, is separated by an angle phi from the point at which we want to determine the MMF. Similarly, this coil is separated by an angle of 90 minus phi from the point where we want to determine the MMF. Now, that is equal to this, and if you look at this expression, it says that you can consider the MMF at this point phi, at this angle phi which is generated, as being generated by a flow of current along an axis which is separated by phi minus delta from the point where we are determining the MMF, and this is 90 degrees minus phi minus delta, which means that this is equivalent to saying that you have a coil along the d axis and you have a coil along the q axis, and let us assume that there is a current here flowing which is ID, and there is a current here that is flowing which is IQ, and this axis is separated from the displaced from the place where we want to determine the MMF by an angle which is phi minus delta, that is this angle, and therefore instead of considering the MMF here being generated by this coil and this coil due to a current I alpha and I beta, I can get the same value by considering a coil which is now placed along the d axis and q axis, which has a current ID and IQ flowing in it, ID being defined by this expression I alpha cos delta plus I beta sin delta, and IQ being defined by this expression minus I alpha sin delta plus I beta into cos delta. So, effectively we are now looking at the system being viewed from this moving set of axes. We are no longer looking at this, but we are looking at the same MMF being generated from this set of axes which may be moving. At this particular instant it is at an angle delta, and therefore now we can define a relationship between ID and IQ as being equal to cos delta sin delta minus sin delta and cos delta times I alpha and I beta. We are doing this only to the alpha and beta terms, we are not doing anything with respect to the 0 sequence term. The 0 sequence term, as we saw some time back, is deemed to be along an axis that is 90 degrees to both alpha and beta, that means out of the plane, and that is not really going to affect the MMF here because this angle is equal to 90 degrees, that is on a different plane, and therefore we transform only the alpha beta to this dq. This is for the stator. We could have done the same thing for the rotor as well, because the rotor also has one coil now, though pseudo stationary, one coil on the alpha axis and one coil on the beta axis. if we want to determine at this angle phi what is the MMF generated due to this current in the alpha coil and this current in the beta coil, you would proceed in the same way and you would get a similar expression for the equivalent flow of currents along the D and Q axis. So you would have put D as a superscript, Q as a superscript, and then this would be IR alpha and IR beta. So both the stator and the rotor have now been referred to this so called arbitrary reference frame. Now again, why is it arbitrary? Because the speed of rotation, that means d delta by dt, delta is the angle made by this d axis with respect to the alpha axis, and if this is going to be rotating, delta is changing with time, and d delta by dt we will simply call it as omega x. We do not know what that speed is. The speed in general, the useful values of speed are, it could be omega s, which is the synchronous speed, it could be omega r, which is the rotor speed, it could be omega 0, which means 0 speed. These are three useful values that are usually then considered in the literature. Let us look at what is the implication of this kind of referring. So in this reference frame we know the expressions for I alpha and I beta. We know that I alpha has this form, some amplitude multiplied by cos omega t, where omega is then the synchronous speed, because the frequency of stator excitation is going to determine the speed at which the MMF revolves around the air gap, which is nothing but the synchronous speed. So that is omega s, and similarly you have I beta equals I m sin omega s into t. So if you substitute these two into this expression, what do we get? You get ID equals Im cos omega st cos delta plus Im sin omega st into sin delta, which is nothing but Im into cos of omega st minus delta. Similarly you have Iq, which is Im minus Im sin delta cos omega st plus Im cos delta sin omega st. This is then equal to Im into sin of omega st minus delta. Now let us first look at the case where d delta by dt is equal to omega s. That means the reference frame is rotating at synchronous speed. So if it is rotating at synchronous speed, d delta by dt equal to omega s means that omega s, or rather delta, equals omega integral of this. So that is nothing but omega s into t, but in order to satisfy the integration we need to add an arbitrary term gamma, which will have to be evaluated based on some initial conditions of the system. That means at t equal to 0, delta will be equal to gamma. So, gamma then represents the angle which the d axis of the reference frame makes with the alpha axis of the stator at t equal to 0. Gamma may be 0 or gamma may be something else. So, if we substitute this expression here, what you get is id equals Im into cos of. So, when you put this here, omega st minus omega st minus gamma. So, you get Im of minus cos of minus gamma, which is Im cos gamma, and Iq is Im sin of omega st minus omega st minus gamma, which is Im sin of minus gamma, that is minus Im sin gamma. That is what you have. What is interesting here is that this expression id and iq are not dependent on the variable t. That means these are basically constants, they are not functions of time. Being that also means now therefore id and iq are DC quantities, which means now that the excitation provided to this d axis and q axis is no longer AC, but it is DC. That is very interesting and has very useful implications when you are trying to design a control system. I think some time back I mentioned that it would be good to have DC variables in the loop in order to have your PI controllers, they work well with DC and you can be assured of 0 error if it is designed appropriately. How much is the DC value, however, depends on the angle which the d axis makes at t equal to 0. One can choose that angle appropriately, you can choose it based on any condition that you want, and if you choose gamma equal to 0, then id becomes equal to Im and then Iq is 0. So, that is again useful to say that if I orient my frame d and q axis, the reference frame, if it is oriented at some particular angle, then you can see that only d axis component exists and there is no q axis component. So, this is one interesting aspect of the development. On the other hand, suppose I choose d delta by dt, that is the speed of the reference frame, as being equal to omega r, then what happens? Then id becomes equal to Im into cos of omega st minus omega rt minus gamma, which is nothing but Im cos of omega s minus omega r into t minus gamma, and therefore this now omega s minus omega r into t is the frequency of flow of excitation flow in the rotor. So, this is nothing but the slip frequency. One can alternatively write this as s times omega s into t, and therefore that is nothing but the slip frequency that is there. Similarly, Iq is Im into sine of omega s minus omega r into t minus gamma, and this is therefore in the slip frequency. That means if you transform yourself to a frame that is going to be rotating at rotor speed, that means with respect to the rotor the reference frame is stationary because both are rotating at now at the same speed, and if they are rotating at the same speed you are then observing all the dynamics of the machine from a frame that is rotating along with the rotor, or so to say sitting on the rotor, then what you see is the excitations that are applied to the d and q axis are of slip frequency in nature. That means anything that you see from the rotor, all the mmf's that are there in the air gap, they all appear to be rotating at slip frequency. The actual mmf is rotating at synchronous speed, but then sitting on the rotor you are also rotating at rotor speed, and therefore with respect to you the mmf's are rotating at synchronous speed. How about d delta by dt equal to 0? That means if the reference frame is stationary, then d delta by dt equal to 0, and therefore delta is a fixed number, and therefore the expressions will simply be id equals Im cos omega t minus delta, where delta is a simple number not a function of time, and therefore id will be at the frequency of the supply, iq is at the frequency of the supply. It simply amounts to rotating this alpha and beta axis by some angle, and this is also stationary. So this is just if the reference frame is not going to rotate and the speed is 0, then it amounts to simply shifting the axis by some angle, and therefore since it is stationary the excitations are all at supply frequency. So with this reference frame then one can choose whatever you want. As I said, for most analysis the synchronous speed reference frame is the one that is of use, and that is therefore called as synchronous reference frame. This, as I mentioned before, it is called rotor reference frame, and this is then the stator reference frame. So these are the cases. Now we have dealt with I alpha and I beta being transformed to id and iq. How about the supply voltages? So in order to get that, what we say is, let us assume that power is invariant, which means that the net power that is given in the alpha beta reference frame can be written as I transpose alpha beta reference frame. I transpose V is the input that is given in the alpha beta reference frame, and what we have here is this I dq is equal to, let us call this as the C matrix, or let us call it more as let us not call it as C we have been using all along, let me call it as D matrix, and let me call it as D11 multiplied by I alpha beta. So if I now want to find out I alpha beta having known id and iq, I need to pre-multiply this by D11 inverse, and what would be the inverse of this? The inverse of this is nothing but the transpose of this, because the determinant is 1, cos square delta plus sin square delta is 1, and therefore we can say I alpha beta equals D11 transpose into I dq. So let us substitute this expression in our expression for the total input electrical power, and therefore this becomes D11 transpose into I dq, and transpose of that multiplied by V alpha beta. This is nothing but I dq transpose multiplied by D11 into V alpha beta, which we can now designate as I dq transpose into V dq, where V dq is then this expression, and one can see that V dq is similar to the definition for alpha beta to dq, and therefore we write V dq equals d11 into V alpha beta. So, the manner in which the I alpha beta gets transformed to I dq and V alpha beta gets transformed to V dq, they are identical. So, having defined this these equations, we now need to see how that impacts our machine description. So, the machine description we have already written down in the stationary reference frame. What we have, basically this equation can be written as you would have seen now many times, can be written as V equals R into I plus L into Pi plus G into I into omega R. That is our expression. So, all these are in the alpha beta frame. L, R and then G and so on. Now, what we want to do is to use those equations. Remember, these vectors have both stator terms and rotor terms. You have the stator terms here, first 3 of them are stator and the next 3 of them are the rotor terms, and what we want to do is define a relationship between we want to transform this to the dq reference frame. So, we want to define a relationship from the stator to rotor. You have Vd, Vq, so we have a relationship which we want to define from the alpha beta to the dq reference frame. So, let us say Vd, Vq, V0, these are the stator terms, and then you have Vd, Vq and V0 which are the rotor terms. So, that is what we have, and we need to define them in terms of V alpha, V beta, V0 for the stator and the rotor. Now, obviously we have seen that the stator equations depend only on stator variables, stator equations do not depend on the rotor variables, and therefore what we can say is here you have cos delta and then sin delta minus sin delta cos delta. 0 sequence, as I mentioned, is unchanged. We do not touch the 0 sequence, it is not necessary to touch that. So, that remains the same, and this does not depend on the rotor terms, and therefore these 3 are 0. When you come to the rotor, you have, it does not depend on the stator 0 sequences or the alpha beta. So, that is not there. Similarly, here you have cos delta sin delta 0 minus sin delta cos delta 0 0 0 1. So, this is the transformation that is then used from V alpha, V beta, V 0, V alpha but R, V beta but the rotor and V 0 rotor. So, that is the expression, and that is why we called this matrix as D 1 1. So, that is the same as D 2 2 also. These are 0 matrices. So, what we can say is V dq. Let us now have this notation dq for the stator and dq for the rotor as well. This is equal to d times V alpha beta on the stator, and the rotor is also referred to alpha beta of the stator. So, this vector we let us call it as alpha beta and then R. Similarly, then we can define I dq is d times I R alpha beta. Using this, we need to look at what happens to the equations, and if we want V alpha beta, then we have to pre-multiply this by D inverse, and because this is a matrix that has entries only in the block diagonal and this term inverse of this itself is equal to the D 1 1 with a superscript T. So, what we can say is D transpose into V dq is equal to V alpha beta R, and similarly I dq and D transpose is equal to I alpha beta R. So, it is these two equations that we need to substitute in this in order to find out our new machine description, which we shall proceed to do so now. So, what we have is we substitute, so D transpose V dq equals R D transpose I dq plus L times P D transpose I dq plus G times D transpose I dq omega r. And therefore, if I want to find out V dq, you have to multiply by the inverse of this matrix throughout, and again inverse is nothing but the transpose, and therefore, this is d times here, d times here and d times here, and therefore, this simplifies as dr d transpose I dq plus, now in this term you have P and then d transpose I dq. This d is also going to be dependent on t with respect to time, that is, and therefore, one can write this as dl d transpose P I dq plus dl P d transpose I dq plus d g d transpose I dq into omega r. Now, in this term P d transpose, you are taking the derivative of d, and d depends on delta, therefore you will get a d delta by dt term, which is then your term which depends upon the speed of the reference frame. So this is the expression that you get, and one has to substitute the terms and simplify it to see what is the effect it is going to have on the equations of the machine itself, which I will leave it to you as an exercise to do. We will look at the final equations in the next lecture. We will stop here for now.